In this video, we're going to do a few examples with open and closed sets. So for the first three examples, we're just going to use R with the usual metric. That's where the distance between x and y is equal to the absolute value of x and y. So for the first, let's let a and b be real numbers with a less than b. Show the interval ab is open. Also show that the interval from negative infinity to a is open and the interval from b to infinity is open. Then show that the typically closed, but meaning containing its endpoints, interval 5, 8 is closed. So basically we're showing things we assume are open, and things we assume are closed in the real line. And then in part 3, is the set 5, 8, so that's includes the endpoint 5 and does not include the endpoint 8. Is that set open? Is it closed? Is it both? Is it neither? So pause the video, think about each of these, grab a piece of paper, and we'll talk about them together. Okay, so for this first one, to show that the set AB is open, there are different options for this, different ways to show that this is true. One of them is to basically show that this is some ball centered at some point with radius r. And we know that the definition of being open is to be a union of open balls. So if something is itself an open ball, then that's the union of one open ball with itself. That is a union of open balls, and therefore it is open. So that's what we want to show. So what is the center and what is the radius of this open ball? So let's let C be b minus a over 2. Then if we think about a and b on the real number line, then the midpoint is a plus c, a plus b minus a over 2, and this radius b minus a over 2 from that midpoint would take us up to a and b in either direction. So this tells us that the open interval AB is equal to the ball centered at a plus b minus a over 2 with radius b minus a over 2. And that is ball centered at that point with this radius. That's all things of the form x in r, such that the distance here, that's the absolute value of x minus a plus b minus a over 2 is less than b minus a over 2. So that is an open ball, and that is the open interval AB. And as we said, since AB is an open ball, it is the union of open balls, and so by definition is open. Okay, and now let's look at let's show that the interval from negative infinity up to a is open. So for this, let's let x be an element of this interval, negative infinity up to a. Because it's in that interval, which does not contain its endpoints, then x is a real number, and x is less than a. So let's say that a minus x is equal to epsilon. Since x is less than a, that's going to be greater than 0. So now what we're going to show is that there's some ball centered at x that's completely contained in that set. So observe that the ball centered at x of radius epsilon over 2 is completely contained inside of the set negative infinity up to a. Because we've got this real number line up to a, x is somewhere, the distance from a to x is epsilon, and we are talking about a ball of radius epsilon over 2. I should really just be drawing this, it's a one-dimensional space or a two-dimensional space that we're talking about, so this is not really making sense. Anyway, so we've got this ball of radius epsilon over 2, and it is completely before A. It is, of course, larger than negative infinity because x is a real number, and so it is contained in that set. And this is, again, by part B of that theorem that we previously proved, that a set is open if and only if, for any x in that set, there is a ball of positive radius that is centered at that point that is completely inside of the set. And showing that the set B to infinity is open is similar, so I'm not going to do the proof, but it's very similar proof. Now we want to show that the closed interval from 5 to 8 is closed in R with the usual metric. So at this point, to show something is closed, one of our only tools is to show that its complement is open. That's the definition of a set being closed. So we want to show that the complement of the set 5, 8 is open. That's what we want to show. So let's look at 5, 8 complement. That would be the union of the interval from negative infinity up to 5 unioned with 8 to infinity. So that's the complement of that set on the real number line. And we just proved that things of this form are open. We said that the proof that things of this form are open is very similar. So this is a union of open sets. And by our theorem, we showed that arbitrary unions of open sets are open, that finite intersections of open sets are open. So by theorem, that means that negative infinity to 5 union 8 to infinity is open because it's a union, an arbitrary union of open sets. And so therefore that means that 5, 8 complement is open, which tells us that the original set 5, 8 that includes its endpoints is closed. That's the definition of a set being closed, that its complement is open. Okay, so is the set 5, 8 closed on 5 and open on 8? Open? Is it closed? Is it both? Is it neither? So first we'll show that this set 5, 8 is not open. How do we know that it's not open? So again, we're going to use that part B of that previous theorem, that U is open if and only if for all x in U there is some epsilon dependent on x such that the ball centered at x of radius epsilon sub x is contained in U. We're going to use that theorem. So note that 5 is in this half-open interval, 5, 8, and for any, well, we could express this in different ways. One is that there exists no epsilon greater than 0, such that the ball centered at 5 with radius epsilon is contained in the set 5, 8. Because as long as epsilon is greater than 0, for example, 5 plus or 5 minus epsilon over 2 would be in this set and would not be in that set. So this condition B does not hold, and therefore this set, therefore the set 5, 8 is not open. All right, how about could it be closed? So let's look at 5, 8. We're wondering whether 5, 8 could be closed. Well, it's closed if and only if its complement is open, if and only if 5, 8 complement is open. And so 5, 8 complement is equal to the union from negative infinity up to 5 unioned with the closed endpoint 8 to infinity. And again, here we have this issue here to show that this is not going to be open. So 8 is in this set, So 8 is in this set, and for any epsilon greater than 0, the ball centered at 8 with radius epsilon is not going to be contained in this set, is not going to be contained in 5, 8 complement. And therefore, 5, 8 complement is not open, and that tells us that 5, 8 is not closed. So this half open interval in the real line with the usual metric on R is neither open nor closed. In the previous video, we stated that in a metric space XD, arbitrary intersections of closed sets are closed and finite unions of closed sets are closed. And you're proving this in the homework. So we're going to show with an example here that infinite unions and also arbitrary unions of closed sets will not necessarily be closed. So here, let's consider again R with the usual metric. And we proved that the closed interval 5, 8 is closed for any 5, 8 is closed above, and you could use a similar proof to show that the closed interval AB is closed for any A less than B in the real numbers. So let's assume that that is true, and that means that the closed interval 1 over n to 1 minus 1 over n is closed for all n in the natural numbers. So we have this. Now, let's find the union from n equals 1 to infinity of sets of that form. So the closed interval from 1 over n to 1 minus 1 over n. So for the first part, just, what's a different way that you could write this set? What's a more simple way that you could write this set? And after you do that, prove that this set is not closed. So once we do that, we'll have an example where we have an countably infinite union of closed sets that is not closed. So again, I encourage you to pause, try this out, and then we'll talk about it. Okay, so what is this union equal to? So we have, things of the form 1/2 to 1/2 and blah, 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 and 1/10 to 9/10 and so on. And so this is going closer and closer to 0. This is getting closer and closer to 1, but never quite hitting it. So the union of these sets is going to be the open interval from 0 to 1. So now we just want to show that that is not a closed set. It might be kind of intuitively clear that this is not a closed set, but let's prove it. So show that 0, 1 is not closed. In order to show that 0, 1 is not closed, we want to show that 0, 1 complement. So want to show that 0, 1 complement is not open. To show that that's the case, let's look at 0, 1 complement. That is negative infinity up to 0, unioned with up to 0 and including the endpoint in the complement, unioned with 1 to infinity. And again, we have the same issue we had previously, that, for example, 0 is in 0, 1 complement, but for any epsilon greater than 0, the ball centered at 0 with radius epsilon is not a subset of 0, 1 complement. So therefore, the set 0, 1 complement is not open, and this implies that 0, 1 complement is not closed. So we have a countably infinite union of closed sets whose union is not closed. And so in general, it is not the case that arbitrary unions of closed sets are closed.